we have two things at play here. Going from top dead center to, actually it's 76 degrees after top dead center, but we'll call it 90 just because of the square angle. Our leverage increases. But as that piston moves down, the volume inside the cylinder increases. And as you increase volume, you decrease pressure. They're inverse of each other. So, if we have a 100 millimeter bore at 2400 RPMs, and we have 12.5 milliseconds to complete a half a stroke, the power stroke, let's see here, 100 millimeters divided by 12.5 milliseconds. That means that at the fastest point, mid-stroke, the piston is traveling at 8,000 millimeters per second, which is 800 centimeters per second. 800 divided by 41.5. Remember, 41.5 was the speed of gasoline flame. So now we got a piston speed, it's 800 centimeters per second. We got a gas that's burning at 41.5. The piston's moving over 19 times faster than the flame front. In other words, the piston is actually outrunning the flame front, and in certain circumstances, there's actually pressure up by the spark plug, but a vacuum on the laminar surface of the piston itself, because the piston's moving so fast, it's creating a slight vacuum there. I guess we're not harnessing much energy there, are we? But wait, it gets worse. So we have 800 centimeters per second piston speed at 90 degrees after, or thereabouts. Let's take a look at the volume increase. Remember that pressure going one way and volume going the other thing? So let's see what the volume increase speed is. 800 centimeters per second times the cylinder area, and if you remember your geometry, that would be pi times the radius squared, and the radius is 4.5 centimeters. So we work out the math, 800 times pi times 20.25, which is radius squared, and we get a volume increase speed of 50,894 cubic centimeters per second. That is 1,226 times faster than the flame spread speed of the gasoline fuel. In other words, we're not really harnessing energy there either. So by about 45 degrees after top dead center, we've harnessed 80% of the total power that we're going to be able to. It's the physics side of it. We're just, the volume is increasing too rapidly to be able to harness energy when it's most advantageous leverage-wise, that 76 to 90 degrees after. 45 degrees crank rotation. Only 15% of the chemical energy in the fuel has actually been converted to power in those 45 degrees. That means that we've just wasted 80% of the fuel. That's why the engine is only 20% efficient. To improve combustion efficiency, you have to be able to convert more of the chemical energy in the fuel going through all those processes to thermal energy, to kinetic energy within that magic window, that 45 degree magic window. When you get that, everything else makes sense. Now, how do we do that? That sounds great. I want to do it. What do I do? Well, we can reduce the endothermic requirements both energetically and time-wise if we can pre-vaporize more of the fuel. Because remember, this first step in extracting energy from the fuel is we have to vaporize it. So heating the fuel. Next, you can have a perfectly vaporized cluster of fuel molecules, but no oxygen, nothing happens. You can have oxygens that are all split apart, but with no fuel, nothing happens. So if you can better mix them somehow, then when an oxygen splits apart and a hydrogen pops off, they're right there next door neighbors, and they get back together, make some water, and make some power. So better homogenizing the fuel. In-cylinder turbulence. you want to be able to ignite the fuel with the spark and then take that flame front and swish it around and send it to the fuel and the oxygen molecules. And then that swishing also brings the oxygen and fuel closer to the flame front, so in-cylinder turbulence will help. Reducing the endothermic requirements to initiate the oxidation process. Something like ozone, ionizing the fuel. We'll cover that a little bit more later. And then deliver only the amount of fuel necessary to make the combustion. We don't want rich air-fuel mixtures here. We want only the fuel we need to get the job done. And then the ignition timing aspect of it. CCA is critical crank angle. The textbooks say on a typical engine that's 17 to 18 degrees after top dead center. Again, we have more leverage as the piston moves down and the crankshaft gets closer to a 90-degree angle, but we also have that increasing volume aspect. So if we can get our peak pressure at 17 to 18 degrees, that is called critical crank angle. And we would adjust that by adjusting ignition timing. And again, we can vaporize more fuel by heating it. Modern day fuel injectors are sitting on top of an engine, and they are designed to handle in excess of engine coolant temperatures. So if we were to heat the fuel to, say, coolant temp, we'd be doing it safely. But I'll cover that in more detail later. Believe it or not, adding magnets to the fuel line. There's a right way and a wrong way, but they can work when done properly. One of the biggest low-hanging fruit improvements you can make is to increase spark intensity. And we're going to cover that quite in detail because it is easy, relatively, it's inexpensive, and you get a big bang for the buck. Adding combustion accelerants. That could be a fuel additive you put in your gas tank when you fuel up. But it could also be something like HHO or ozone. And then better homogenizing the air and the fuel. Things like what we're going to cover, Gadget Man Groove today. There's the little air spinny thingies, and there's, again, a right way and a wrong way to use those, but when done right, that can better homogenize. And then actual engine design, manifold and engine design, which we'll touch on. And then, again, improve the intake and also the exhaust system. You can improve in-cylinder swirl with exhaust design by jump-starting the process in the process of evacuating. And then intake, it just swirls around as it comes in. Electrochemically destabilizing the air or fuel. So a fuel ionizer, something like the fish fuel catalyst, destabilizing the air like an ozone or ionizer type device. And then increase the compression expansion ratio. Grounding the exhaust system. Can't wait to hear about that one, huh? Improve the PCV system. The PCV system is taking stuff that doesn't burn very well, putting it back into the charge, slowing it down, increasing the pollution level. So there's a lot that can be done there to improve combustion. And then tune for those improvements. All the modifications in the world won't do much good if your spark timing's off, if your fuel ratio's off, so basic tuning for it.